well, and a source for confusion at times. We'll try to make it simpler. So here's the definition of a polynomial function. I'm just going to write it down and then I'll explain what all those things mean. It looks a little scary, but it's a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus all the way to a sub 1x plus a sub 0. Looks a little weird, but that's okay. And these are all n's. I know they look h's at times. Those are all n's. So the subscripts, those are just the way to distinguish real numbers, and the superscripts, I guess if that's what you call them, those are exponents. Okay, so n is just some natural number. No, those are all n's. All of them are n's. I know some of them look like h's. So n is a natural number, and all those a sub whatever belong to the set of real numbers, so those are just real coefficients. So that's what you expect from a polynomial. Real number times the variable raised to a positive exponent, positive integer exponent. Okay? So we say that this is the nth degree polynomial. So whatever the highest power is defines the degree of a polynomial. If the highest power is 11, so that's 11th degree polynomial. Doesn't mean whatever the first power is, because we can rearrange them. Does not change the fact of what the highest power is. Okay, so it's the nth degree polynomial. This front, the first term, the term that carries the highest power, that's the leading term. It's just some verbiage. So the leading term is whatever carries the highest power. A sub n by itself, that's the leading coefficient. And that guy in the end, the one that does not have a variable, a sub 0, that's the constant term. Okay? So that's just some verbiage. So I'm going to write something down, and you'll tell me the degree and all that good stuff. Okay, so for example, if I write something like this, f of x equals negative 3x to the 5th plus 11x squared minus 7x plus 2. First of all, is that a polynomial? Yes. Basically, what you're looking after are negative exponents. No, it's not a polynomial. Fractional exponents, that's not a polynomial. Denominator with variables in it, that's not a polynomial. But yes, it is a polynomial. What is the degree? Yeah, so it's a 5th degree, the highest power that you see. What is the leading term? Well, negative 3x to the 5th, the whole thing, right? So the leading term is negative 3x to the 5th. The leading coefficient is negative 3. Okay? And what is the constant term? 2. So whatever the constant is. The important parts here are being able to identify the degree and the leading coefficient. Because later we're going to try to graph them, and we'll see the pattern that all odd degree polynomials look this way, and all even degree polynomials look this other way, but there's a similarity. And also whether the leading coefficient is positive or negative, that gives you, remember if you put a negative in front, something flips, yeah. So that would be the 5, the highest power that you see. Oh, it's just negative 3, because those lower ends, the subscripts, they don't mean anything. That means it's some number. This number probably different from that number, so that's all it is. We use Yeah, we use subscripts to distinguish between constants, and we use, those are exponents, so those actually have meaning. So superscripts, meaningful, subscripts, not so much. Yeah, that's all it is. So it doesn't mean that there's a certain pattern. All the n does that, this n is attached with that n. That's kind of all that matters. So the leading coefficient is whatever, so the n corresponds with the exponent, so whatever's attached to the highest power. So yeah, when you look at the constants, that subscript is meaningless. It just tells you that's a constant. Okay? All right. So here's another one. 11x minus 4x cubed plus 12x squared. Can you tell me the degree? Right, so degree is third. Don't fall for the trick. Doesn't matter which order, you go after the highest exponent. So what is the leading coefficient? Right, so leading coefficient is -4. So that's going to be the most important part when graphing these things, is the degree and the coefficient. And mostly odd or even degree and positive negative coefficient. So they'll define the shape of the graph and where it starts and so forth. What about the constant term? What is the constant term here? 0. Because again, you're looking for something that does not have x attached to it. You don't see it, so it's 0. So 0 is a constant term. Yeah. It's going to be -4x to the third. So it's whatever carries the highest power, yeah. So again, the order doesn't matter. You go by the highest power. Any questions? Good? All right. So let's talk about graphs. The graphs of polynomial functions are pretty. They're nice, smooth. By the way, smooth is a mathematical term. It means it's nice and pretty, really. That's, some of you might study more precise definitions of smooth graph, but there are no sharp edges. Everything is nice and curvy. So like absolute value is not a smooth graph. It's got a sharp edge, the letter V or whatever. But polynomials will not have those sharp edges. They will not have the discontinuities. It's going to be nice, pretty, continuous, smooth curve. So the graphs are pretty. Okay. So now don't write anything down. I'm going to put down a question and we'll discuss. So here's an example of a polynomial function. 2x cubed minus 3x plus 1. Don't write this down. I want to ask you, what do you think happens with this function, with the values of this function for larger values of x? I don't care about for small values of x, but I'm talking about when x gets really, really big. Which term here will really define the shape of this function, basically? The first one, right? The one with the highest power. Because let's say if I take in 100, x equals 100, and I plug it in here. So what do I get? 100 cubed, that's how many zeros? That's 6 zeros, right? 2 zeros cubed, 6 zeros. So that's 2 million, right? If I plug in 100, so it's 2 million minus 300 plus 1. Who cares? Minus 300 plus, it's basically 2 million, right? If you have $2 million in your bank account and you just spend $300 marker and you got $1 rebate, you're still going to be telling people I got $2 million in my bank account, right? Who cares? $300 plus or minus. And really, if I go further, if I plug in 1,000 cubed, that's 9 zeros. What kind of number is that? What? Is that a billion? Oh, I think trillion is 12, right? Billion is 9. Anyway, so it's a billion. Take away $3,000, you know, it's still a billion, right? So in the long run, this graph of this function will just look like x cubed. In the long run, as x gets large, the y values will just skyrocket. They will just go to infinity. Because those smaller terms don't make that big of a dent in that high exponential expression. For smaller values, yeah, you know, you plug in 5, then, you know, there are big differences. But if you start plugging in large numbers, in the end, the graph of this function will shoot to infinity, so it will look like x cubed. Remember the graph of x cubed. This is x cubed, right? And that's exactly what this function looks like in the long run. Around the zero, whatever can happen, but in the long run, eventually it will shoot all the way to infinity, and it will fall all the way to negative infinity. You plug in negative 1,000, you'll get negative billion times 2, and then the rest doesn't matter. It's still all the way down. Does that make sense? So in the long run, odd degree polynomials will look like that. So even if power 13 doesn't matter, it will still shoot to infinity, shoot to negative infinity. So in the long run, all odd degree polynomials will look like your cubic. The even degree polynomials will look like your parabola in the long run. Because again, that first term, if I change this power to something even, then you know you start plugging large values for x. Doesn't matter positive or negative, it goes to positive infinity, right? And those other terms don't make that big of a dent to bring it down. So all these functions will just shoot to infinity. Are you buying this little story? What I'm trying to say here? If I go ahead and plot some of them, let's make it cubed. What did we have? 2x cubed minus 3x plus 1, right? Something like that. So yeah, I mean, for small values, some things happen in the middle. We'll talk about them later. All I want to know what happens in the long run. And if I zoom out, I mean, it just does the cubic thing, right? It falls down and goes up. If I changed my axis to make it a little prettier. So again, we'll talk about this area later. For now, I just want to know what happens in the long run, and that's kind of what's happening. The cubic functions will all look the same in the long run. The quadratic functions or even functions will basically look like parabolas. Something funky happens close to 0, but as you get away from 0, it all just shoots to infinity, and it will never come down. Okay, so are you buying that? All right. So end behavior, I'm going to call this. So end behavior of graphs of polynomial functions. So there are 4 options. Let's do n is even. And here we'll do n is odd. And here we'll do a sub n is positive, a sub n is negative, meaning the leading coefficient. So in the long run, if you have a polynomial function of even degree with a positive leading coefficient, it's going to look just like a parabola in the long run. Okay? Even degree, positive coefficient. Whatever happens in the middle, I don't know yet. But in the long run, the function shoots up and goes to infinity. Because of that first highest power will just kill all that other junk. Now at the same time, if n is odd, and you have a positive leading coefficient, so you just look like a cubic function in the long run. Something happens in the middle, I don't know, but in the long run, it goes up to infinity on the positive side, negative infinity on the negative side. So basically, it's a cubic. There's tails of a cubic function. Something happens in the middle, we'll just cover that later. But for So now we just want to get end behavior done. Now, what happens if you change the sign of the leading coefficient, meaning you're putting a negative in front of the function? So it flips somehow. So you just have an upside down parabola or a flipped cubic. So that's the end behavior. So all you really need to remember that all even functions act like parabolas, all odd functions act like cubics in the long run for extreme values of x, either positive infinity, negative infinity. Does that make sense? So another way we can describe this, I'm just going to focus on this one tail here, because I'm sure you're going to get questions that are similar to this. So what happens to the values of your function on this end? What happens to the values? Can you describe it? Are the values getting large or small or negative, positive? As you keep moving in the positive x direction, what happens to the y values? Negative, right? So we can describe this mathematically. You can say f of x goes to negative infinity. This is kind of a notation to show where it's heading as x approaches positive infinity. So as x moves in a positive direction, the y values go in a negative direction. That's what this thing tells me. I can describe this behavior by saying the values of the function go to the positive infinity as the values of the variable go to the negative infinity, right? As you're moving in the negative x direction, the values of the function are going up for that particular graph. Okay? So, there's one little connection we need to make between, remember we introduced the concept zero of a function? That was a few weeks ago, but that was the idea, whatever makes a function equals zero, right? Now, there's a certain ways I can paraphrase that statement. So I'm going to give you the list of 4 equivalent statements. Equivalent statements mean if you have one, you have the rest of them. They all mean the same thing. One implies the other 3, and one of the other 3 implies the. So I can, one implies the other. If you have one, you get all 4 for free. Okay? So here's that list. Some of them might look weird, but let p of x be a polynomial function. Then the following 4 statements are equivalent. Here's the first statement. X equals A is a 0 of P of X. So let's say we have that given. So A is a 0 of P of X. Okay? Then if that's the case, then also X equals A is an x-intercept of the graph. What? Oh, you hit the wall? Are you falling asleep there? All right, sorry. What? One just fell asleep, the other just walked out. So anyways. So again, basically what this tells me, if x equals a is a 0 function, then x equals a is also an x-intercept. What do you think of that? Because if, what it means, if x is a 0, I mean, if a is a 0, if I plug it into the function, I get 0, right? That means the y value equals 0. Now, if you look at the x-axis, if the y value equals 0, then the point is on the x-axis, because that's the x-intercept, and vice versa. Whatever you hit the x-axis, that's the 0 of the function, because that's what makes your function equal 0. At the same time, x equals a is a solution to equation p of x equals 0. I mean, that's just basically going from the fact that x of a is a zero function. That means it should solve this equation. If I plug a in here, I should get 0, right? And the fourth statement, and that one is a little tricky. Basically, x minus a is a factor of p of x. And this one is really, you can see it kind of one way. If it is a factor, then it has to be 0, because you said your polynomial equal to 0, and so you said factors equal to 0, right? Going the other way is a little tricky, and this is kind of the glue that holds the fun sections together, the sections 4.3 and 4.4. So for those of you who are planning on doing those sections, you'll remember that statement. But for our purposes, all we really need are the first 3 right now to get a sketch, because we go from zeros to the x-intercepts and back. And question? You're just checking out? Okay. We were just sitting like that. Anyways, so you'll see me playing with these statements. Yeah, the facts will come in place. But anyways, the bigger focus on the fourth portion is in the next few sections. So let me give you an example. Here's a function, f of x equals 2 times x minus 1, x plus 4, and x minus 3. Because if I ask you, find zeros of this function, how would you go about it? How would you find zeros of a function? Yeah, because you're going to set the whole thing equal to 0, and since it's already factored, you're going to set each factor to 0, so the zeros of this function are positive 1, negative 4, and a positive 3. And this is that's the first statement. If x minus 1 is a factor, then 1 is a 0 of this function. At the same time, this numbers 1, negative 4, and positive 3 are also x-intercepts. So I already know the x-intercepts. So they'll help me sketching the graph of this function. Now check this out. 2 doesn't really do much. 2 just stretches the graph, so I don't care. But look at that. I already have the x-intercepts. 1, 2, 3, 4, negative 4, positive 1, and a positive 3. Right? Now I just need to connect those dots. So I know for sure that the graph will go through these points. Right? Now, how it's going to do that? So there are really 2 options. There are 2 options that can happen. I can do something like that, right? That's a pretty smooth curve that hits all the points. Do you agree with that? All right. Or I can do something like that. That's another pretty smooth graph that hits all the points. So how do we know which one it is? That's where the end behavior comes in, because all I need to know is it going to be down up or up down. Which version is that? So let's identify the key points that we need in order to determine the end behavior. I need to know the degree. What is the degree of this polynomial? What do you think? Third, right? Because again, by the definition, the polynomial has to be in the extended form. So if I pretend foiling this whole thing out, the highest power that I'll see is x cubed, and I don't care about the rest. So that's a third degree. And the leading coefficient, what is the leading coefficient? Not even the leading coefficient. What is the sign of the leading coefficient? Positive or negative? What do you think will happen? Again, just pretend foiling without really foiling. So you have x, x, x. That's your x cubed. Then there's that 2 on the outside. So that's 2x cubed. So is it going to be positive or negative? Positive. So it's an odd degree polynomial with a positive leading coefficient. So this is the only option that can happen. Does that make sense? There's no other option here. Is that okay? Now we're also going to learn that, I mean, how many zeros does this thing have? How many zeros? 3. So a third degree polynomial will have at most 3 zeros. It can have 1 0, but it's going to be repeated there like 3 times. The exponents are always going to adopt to the degree. So a third degree polynomial has at most 3 zeros. So in general, we can make this quick statement that nth degree polynomial has at most 3 zeros. Yeah, I mean 3, no, not 3, n, because I'm going for the general. Sorry. It's not just all polynomials have n, and 3 zeros. So the 12th degree polynomial, potentially 12 different zeros, potentially 12 different x-intercepts, and so forth. Now also, these are, let's call them turning points. So here's the extreme case, third degree polynomial, 3 zeros. How many turning points? 2. So it's always 1 less. Okay? So nth degree polynomial what? At most n minus 1 terms. It's not that important. On the homework, you might get a question. Hey, here's a 7th degree polynomial. What is the maximum number of terms it can have? And you say, well, 6. Okay, move on. That type of stuff. So the number of zeros, same as the degree. Number of terms, 1 less. All right, but anyways, let me take the same problem, same question that we just did. And I'm just going to play with that a little bit. So I'm going to take this problem, and I'm going to, I don't know, I'm going to square this one, x plus 4 squared. Okay? Did that change the number of zeros? What are the zeros of this function? What are they? I mean, can you tell me? I mean, that's the same as what we just did. What are the zeros? 1, negative 4, positive 3. What? Yeah, 3 zeros. Still 3 zeros. They're still the same zeros. So we're still 1, 3, negative 4. We're still hitting these points. But what is the degree of this polynomial? 4th. So the degree is 4th. And the leading coefficient is still positive, right? So it has the different n behavior. It has, well, it has this n behavior, right? It's an even degree positive leading coefficient. You agree with that? Well, now when I try to connect the dots, it doesn't quite, right? I mean, what just happened? Oh yeah, I created something that wasn't there. There's no x-intercept there. I'll just wait till it go away. Because, you know, it's magic. All right. So I have to come down, come up, and then when I hit that one, well, I cannot turn around, right? Because if I turn around, I'm creating an x-intercept that's not there. Do you agree with that? I mean, like, how do you connect the dots and you end up with the end behavior? Something has to happen here. Yeah, so it has to just touch the x-axis at some point. And just take a wild guess. At which 0 will the touch occur? Just take a wild guess. -4. And actually, what we're also going to learn that locally, oh, look at that. Locally, these factors are going to look just like the functions themselves. What is x plus 4 squared? It's a parabola shifted 4 units to the left. So you're going to have a tiny parabola shifted 4 units to the left at 4. The rest of them are linear, so you're going to have just straight lines going through the rest of them. If I make one of them cubed, you're going to have a tiny cubic that shifted 3 units to the right. So locally, they're going to look just like those functions taken apart. But for our purposes, the graph of this function is going to come down, bounce off -4, so making a little parabola. Then at some point it has to turn around and then just cross the x-axis as we did before. So locally, if you zoom in, this looks like a little straight line. This looks like a little straight line. That looks like a parabola. And this is what the graphs of those factors individually are. Straight line, a parabola. Do you see that pattern? Okay. Let's change this one more time. So I'm going to do, what did I do with my notes? Doesn't matter, but that one was power 4, that one was power 3, that one was power 5. So did that change the number of zeros or the number of x-intercepts? Still same intercepts, just it's going to be a whole lot funkier in there, but we're still going to hit the x-axis at 1, 2, 3, 4, at -4, at +1, and at +3. Right? What is the degree of this polynomial? What do you think? 12. Really just end up hitting all the exponents. Because again, you're pretending, foiling it all out, so x to the 4 will come out of that one, x cubed will come out of the middle one, and then x to the 5th, and at some point you'll have to multiply them, and you'll just have the exponents, and get x to the power 12. That's a little complicated, just add all the powers. Okay? So if you add all exponents of your factors, you get the degree of that polynomial. So 12 degrees still positive leading coefficient. So it still has the positive leading coefficient, even degree, type, and behavior. What? Are you enjoying this? Well, it's going to get really weird, but x to the power, the 4th power, that's still like a parabola. It's kind of a fat bottom parabola, but still a parabola. So it will still bounce off at, no, the cubic is an odd one, so let me take it back. So when I look at this one, that's a cubic, right? What cubics look like? They look something like that. They just kind of wiggle through the x-axis, just like a cubic function. Then it has to turn around and come back, touch at 1. Now at 1, you're going to have a 4th power function, which is still like a parabola. It will do that. It will draw a little parabola there. And then we'll come back, and we'll give you another cubic, so something like this. So just again, locally, even powers, they're all parabolas, odd powers, they're all cubics. And linear or linear, okay? Now your book puts it in a different notation. They're going to say, well, let's define a notion of a multiplicity of a 0. So whatever the exponent is, it defines the multiplicity of a 0. So let's say x equals 1 is a 0 of this function with multiplicity 4. X equals -4 is a 0 of this function with multiplicity 3. And x equals 3 is the zero of this function with multiplicity 5. Yeah? And basically, if it's even multiplicity, it will bounce off the x-axis. If it's odd multiplicity, it will go through the x-axis. It will kind of wiggle through the x-axis. If it's 1, then it goes like linear. Does that make sense? So we're going to, yeah. Well, it only has how many terms? 3, yeah. Well, at most n minus 1, right? So 12-degree polynomial can have 12 zeros. It only has 3 zeros. And it can have up to 11 terms, but only has 3. Okay? Yeah. 2 doesn't do much. Oh, you're just paying attention to the sign of it. That's all it does. If I make it negative 2, then it just flips everything. Right? I mean, if I try to use foo plots on this function, it'll just look bad. Because because I don't know how low it goes, I don't know how high it goes, but if I type in 2 times, I don't remember, x, what is it? X plus 4, right? To the third, and then what? I don't know if I need to put my times. Yeah. So I mean, generally it's not correct. Doesn't it? We're not doing anything at negative 4. Yeah, see, there's no information there. Why didn't it touch negative 4? Full plots. See, that's correct. Bounced off. That's correct. Went through. Why not negative 4? Oh, here we go. I guess I had to put the times symbols. So now it's hitting negative 4. Where is it? Now look, if I really zoom in, it's supposed to do a little wiggly thingy. Does it do a little wiggly thingy? Yeah, you see? It does a little wiggly thingy. But you see, I'm really zooming in. Here we go. Yeah. But I'm really zoomed in. So if it's greater than 1 and odd, it'll do the wiggly thingy. If it's 1, so again, linear, odd, cubic, even, quadratic. That's all, you know. Whew. Foo plot. Okay, so definition. If x minus a to the power m is a factor of a polynomial, then we say that x equals a is a 0 with multiplicity m. So whatever the power of a factor defines the multiplicity of that 0. Okay? So if m is even, then the graph bounces off the x-axis at x equals a. So it either looks like this. No, here's a, so it either bounces off, or top or the bottom. You don't need to predetermine that. When you connect the dots, you'll know. If you approach from the bottom, you bounce from the bottom. If you approach from the top, you bounce from the top. And then if m is odd, then this what can happen. Now here's a, just straight line. That's if the multiplicity is 1, so it's linear. Or like that. or like that if m is greater than 1. So again, linear, quadratic, cubic. That's all you need to remember. Linears, so powers of 1, all straight lines. All evens are quadratic, so they're parabolas, parabola-looking thingies. And odd ones are all cubic, so do a little wiggle. How's that? No. M is, we don't do M is less than 1. No, it's just, they're all odd. M is 1 or greater than 1. So if it's 1, it's linear. If it's greater than 1, then it's... Yeah, well, if M is less than 1 or whatever, if M is negative, then it's not a polynomial. We like our exponents to be positive. Is that right? Try this one. I'm going to give you this example. I just lost it. So things are nice when it's already factored. Negative 2x minus 2 squared, x plus 4 cubed, x minus 3, and x minus 5 to the 4th. So first thing that I want you to do, list the zeros with multiplicities. So basically, do this kind of table. So these are the zeros, and these are the multiplicities. That shouldn't be hard. What are the zeros here? Anyone? 2, negative 4, 3, and 5. What is the multiplicity of 2? 2. You just look at the powers. What's the multiplicity of negative 4 and negative 3? I'm sorry, positive 3. Well, 1. And 5? 4. If you add all the multiplicities, that's the degree of this polynomial. The sum of all multiplicities will tell you the degree, so it looks like 10. So it's even degree, negative leading coefficient. So we know the end behavior of this polynomial. I can sketch the graph of this polynomial. 1, 2, 3, 4, negative 4, and then 1, 2, 3, 4, 5. So what do we need? 2. Oh, this is going to get tight in there. 3. Yeah, I need to redo my scale. It's a little crammed in there. 1, 2, 3, 4. 1, 2, 3, 4, 5. So what do I need? 2, 3, 5, and negative 4. And we're going to start on the bottom, and we're going to end on the bottom. Because that's even degree polynomial, negative leading coefficient, so the end behaviors of upside down parabola. Right? Okay. So now let's start connecting the dots. So as I'm approaching negative 4, what's going to happen? How am I going to cross it, bounce off, wiggle? What's the multiplicity of negative 4? So it's a wiggle, right? So it's like a cubic. Then I need to turn around and hit positive 2. What's going to happen with positive 2? Bounce off, because the multiplicity is even. Now I need to turn around and hit 3. What's going to happen at 3? Just go straight through like a linear thingy, right? Because it's linear. And I need to turn around, and now you know the end behavior. So you know it has to bounce off. So you end up down there. So that weird looking thing is the graph of that function. I mean, close enough. I don't know how high it goes, how low it goes. There's no way for me to find out the location of those turning points yet. We don't have that technology yet, but at least we can get a sketch. Now, the point of this sketch, why this, this quick sketch kind of helpful. What if I ask you this question, so solve this inequality. This whole thing less than 0. So all we have to do, when is the graph below the x-axis? Right? These are the points where the value of the function are less than 0. And that. So I can say, well, on the interval from negative infinity to negative 4, the graph is going to be below the x-axis, meaning the function is strictly less than 0, right? Where else? This is a little tricky. Since we're strictly less than 0, it has to go from 3 to 5, not including 5, because that's equal 0. But still, I can go from 3 to 5, and then union from 5 to infinity. I kind of had to remove 5. If I had less than or equal to 0, then I don't have to. I'll just go from 3 to infinity. But again, basically the question becomes, when is the graph below the x-axis? That's technically, I just covered section 4.6, nonlinear inequalities. With a quick sketch, you can do that really fast. All right? Okay. Good. I'm done. There's one thing left. I don't want to talk about it yet. We'll talk about it on Wednesday.